we have R134A, which is the type of refrigerant we are using, is at a pressure of 2 bar. So we know the saturation pressure. What is the saturation temperature? So at a pressure of 2 bar, so if you look at the pH chart, by now you should be an expert in reading the pH charts. So on one side, we've got the pressure in bars, and on the other side, we've got the pressure in megapascals. So let's find 2 bar. So let me draw at 2 bar. Okay, so at 2 bar, it says what is the saturation temperature. Now, previously, last week when we covered the pH chart, we've looked at the temperature pattern. So for instance, if I follow 60 would be doing here, and if you follow the line straight horizontal, it's still 60, and if you come out and follow the line, it's still at 60. So every temperature is doing that way, and each suction pressure will have a dedicated suction temperature. So by actually looking at the suction pressure, you can automatically read the suction temperature which relates to that. So what temperature, so if you look at the line, the horizontal line we've just plotted, okay, what temperature do we see here?
-10.
-10. So again, I have given you the answer. If you look at the answer here, it says -10. Yeah, so all you have to do here is find the pressure, which is 2 bar, draw a horizontal line at the 2 bar, and you can easily read the temperature, the suction temperature, which relates to the suction pressure. So -10 is the temperature, the suction temperature, or saturation temperature that we want to read. So that's the question 1 answered. And number 2, it's very, very similar. Again, we have the same refrigerant, R134A, and is condensing at 40 degrees C. What is its saturation pressure? At 40 degrees C, so we have to find where 40 is. So if you look at these temperatures, where is 40? So 40 is somewhere here, right? So again, if we draw a straight line from where 40 is, draw horizontally to read your pressure. And what pressure do we have?
10 bar.
10 bar. And if you look at the answer, it says 10 bar. Okay. So question 3 says that we have R134A, which boils at -10 degrees C. So we are in the evaporator now. What is its saturation pressure? So we know our saturation temperature, which is -10 degrees C. So again, all you have to do is find where -10 is from these temperatures. From these temperatures, where is -10? -10 is here. Okay, so all I have to do is at -10 draw horizontally a straight line and read my pressure, suction pressures, which is 2 bar, right? Can you all see? And it says 2 bar.
I think that and question 1 is the same question, though.
The other way around, yes. In the other one, I gave you the pressure where you have to read the temperature, but here I gave you the temperature where you have to read back the pressure.
Yes.
So it's just to show the correlation between your suction temperature and suction pressure. Either way, if you know one of the parameters, you can directly know the other. So we have the same refrigerant. So throughout, we're using the same refrigerant, R134A. So R134A is in a refrigeration system. At one point, a pressure gauge reads 6 bar. So we know the pressure. And the fluid is measured at a temperature of 40 degrees C. We also know the actual temperature. What state is the refrigerant? Okay, so what do? Let's just transfer the information that we have there. So 6 bar, the actual temperature is at 40 degrees C. So where is our 40? Our 40 is here. And if you follow the line 40, it crosses our pressure line there. Okay, now last time we've divided the pH chart into 3 regions. The first region was anything on this area. The second region was inside the dome-shaped circuit. And the third region that we've looked at was anything on the right-hand side of the dome-shaped circuit. So this was region 1, this was region 2, and this was region 3. Okay? And what did we say in region 1? What do we have in region 1?
Subcooled liquid.
Yeah, so subcooled liquid. So meaning anything on this region, it is liquid, subcooled liquid. And inside circuit, inside the region, what do we have? So it varies from all the way to saturated liquid on the left-hand side. And if you move all the way to the right-hand side, it is saturated vapor. And anything in the middle, it is mixed. So for instance, if we take P 0.2, that means at that point, it is 80% liquid and 20% vapor. And if we take that value here, it tells us at that point, we have 80% vapor with very few drops of liquid. Okay, so that's the second region. And then the third region, what did we say? So in the second region, it is mixed. And in the third region, what do we have? What did we call that third region?
Superheated vapor.
Yes, superheated vapor region. Okay, and now if you look at the question, it says what state is the refrigerant? So as you can see, we are here, yeah, which is in the third region. So therefore, the answer is a superheated vapor. So we are in the superheated vapor region. So the state is a superheated vapor. It's slightly different than what we've just covered. So question number 5 says that R134A is at a pressure of 8 bar. So let's use the information that we have. So 8 bar. Let's find where 8 bar is. 8 is here. If I can use 8 bar. 8 bar with a 10K superheat. So we know the degree of superheat here. What are its saturation and actual temperature? The degree of superheat based on T actual minus T sat, which is the saturation temperature. So we know 10. Do we know the actual temperature?
No.
No. What about the saturation temperature? Yes, we do, because you know the saturation pressure, and every saturation pressure has its saturation temperature directly. So where we put our line for 8 bar, it's just a matter of reading what temperature he is. What temperature do you think that is? Around 31, 32, would you say? It's slightly above 30.
Yeah.
Yeah, so we know our Tsat, which is, so TA minus, let's say, 32 degrees C. Okay, so we can calculate our TA, right? TA is 10 plus 32, which is 42 degrees C. Okay, so if you look back into the question now, it says, what are its saturation and actual temperatures? Our saturation temperature, which directly relates to the pressure, which we will read it from there, it's 32 degrees C. And the actual temperature, using this formula, we worked out it's around 42 degrees C. And if you look at the answers, it says 32 and 42 degrees C. So now that you know how to calculate the degree of superheat, we'll also look at the degree of subcooling at some point. You should be able to tell me what number 6 is. So let me read it. It says for 134A at 0 degree saturation temperature. So we know the saturation temperature. And minus 10 degrees C actual temperature, determine the enthalpy of the refrigerant. So what do we have? So we know two information here, the saturation temperature and also the actual temperatures. So our 0 is there. So if I can draw a horizontal straight line from where our temperature is, and the other information that we know is our actual temperature, minus 10 degrees C. Yeah? So we are in the evaporator, so we are subcooling, in the subcooling region. So where is minus 10? So we are in this region. Okay, so if you follow minus 10, so 0 is here, and minus 10 is here. So if you follow minus 10, the point at which the pressure and temperature, the two temperatures, the saturation and actual temperature, crosses. Okay, so if I drop down straight from here to read off my enthalpy. So what do you think that enthalpy value here is? Around 190, yes. So around 190 kilojoules per kilogram. So it's also readable. Okay. So 190 is the answer. Who wants to do number 7, which is very similar to what we've already done? The first information that we have is the pressure at 1 bar.
Yeah.
Right?
Yeah.
So if I can draw a straight line at 1 bar. Yeah. And then look at the next question, the next parameter given.
Yeah,
we
20K.
have 20K. What do we have 20K? What is this 20K?
Temperature, superheat.
Yes, superheat. So we're going to use the same formula as what we've used previously. So degree of superheat is equals to T actual minus T sat, right? Now, we know our degree of superheat, which is 20. Do we know our TA and Tsat? If we know our saturation pressure, you also know your saturation temperature from the pressure. So at 1 bar, we plotted. So if you look at the temperature where our line 1 bar is, what temperature do we see? So it's between minus 30 and minus 20.
27-ish.
Do we say 27?
Right.
So, yeah, so at this point, we don't know our TA, but so our TA is unknown, minus our Tsat is around minus 27, did we say?
Yeah.
Yeah? Okay, so can we calculate our TA?
It's, -7.
Yes, minus 7.
-7.
Minus
Yes.
7. Right,
So don't
yeah,
forget, minus and minus becomes plus. And then if we move that to this side, it becomes 20 minus 27, which is minus 7. Yeah, so now we know our actual temperature. So where do we have our minus 7 here? Is between 0 and minus 10, right? So somewhere here is where our minus 7 is. So if we follow it down, we will cross the line somewhere here. Can you all see that?
Yeah.
So minus 7 is between minus 10 and 0, so I'm following the line, and we're going to cross somewhere here, our pressure line. Okay, now all we have to do is use our ruler to drop down so we can work out our enthalpy. And so the question says, what is enthalpy, specific volume, and entropy of the fluid? So enthalpy is around 390, between 390 to 400. You can give me any values. I think I went with 400. So our H is 400 kilojoules per kilogram. And how do we get our specific volume? Can you see where our specific volumes are? Is those dotted lines here. Those are our specific volume. So if you go back to your first point and find the closest and you read it off, which is 0.2. Yeah? Can you all see that?
Yeah.
Okay.
Yeah.
That's our specific volume. And our entropy, again, these are our entropy lines. And if you follow, find the closest, which is, so the line is between 185 and 180. So if you take the average somewhere here, it'll be 183. So entropy is around 1.83 kilojoules per kilogram Kelvin, and specific volume were around 0.2. They are 400, 0.2, and then 1.83. Question 8. Yeah, thank you very much. So let me read the question, and then we can do it together. So what is the state of the refrigerant at 3 bar and 240 kilojoules per kilogram enthalpy? So what information do we have? What do we need to do?
So at 3 bar, draw a line right across.
Yeah, so at 3 bar.
And then it says enthalpy of, where is it? 240. So just draw vertically straight down.
Thank you very much. So let's find where 240 is. Would you say it's somewhere here? So we can draw somewhere here, would you say?
Yeah.
Yeah. So if I can, I'll draw vertically until I cross my pressure.
And then looking at the second section.
Yeah.
This little hoop thing, whatever it is, it would be closer to the liquid side, but it's not completely saturated, so it will be predominantly liquid with a bit of vapor.
Yes, definitely. So so this point is the one that we're looking at. So the question says, what is the state of the refrigerant? We are around 80% liquid with very, very small droplets of vapor. Mostly liquid with very few bubbles of refrigerant, of gas. Okay, and that's the question answered. What do you have? Mostly liquid with very few vapor. And of course, if you answer number 8, you can directly answer number 9. Okay, so if those values determines our quality, 0.1, 0.2, 0.3, 0.4. And if you look at the line that crosses our line between the pressure and enthalpy is 0.2. So what does it actually mean? So it means 20% is gas and the remaining 80% is liquid, and that's where it's given here 20 and 80%.